So mostly, I would say most applications you're only using argon for TIG welding. There are some argon-helium mixtures, but they're very infrequently used. So when welding TIG, back to it, mostly inert shielding gases to protect the tungsten and the weld pool. Pure tungsten and helium mixtures are standard for use with TIG, if necessary with a DC electrode negative. Zirconiated tungsten electrode are usually used for TIG AC welding, and TIG filler wires are cut into lengths of about 1 metre, and can be pure or a mixed alloy with some silicon alloys as well. It's normally used to try. It's normal to try and use a filler mag that closest matches exactly the same as with MIG welding. The TIG process gives a high quality weld. We've often seen it on bicycles. Those welds around the headstock, they've got nice welds on them. Don't really come across many welds in everyday use or on our own private use, apart from perhaps on motorcycle, on bicycles. That if you look at it, they tend to be very nice welds. TIG process gives a very high quality weld, normally very low defects. But the tungsten electrode is allowed to touch down in the weld pool, and you're going to get contamination in the weld. So it's very important not to touch down the tungsten. Once it's contaminated, you can't use the tungsten again. It's very difficult to get a stable arc once you've touched that tungsten down. Other welding problems are liquidation cracking. As we said before, it's sensitive alloys and that tenacious oxide. Any grease or oil, as it's been said before, is not conducive to a good weld. Some TIG machines are pulsed TIG, so it's giving you a high current and a low current just to give you the ability to get the heat into it, but obviously not have too much heat in it. So it pulses between the high current and low current. So pulsed power sources should have a constant current or drooping characteristics. So it gives that AC or a DC output, depending on which type of current is required, but most of it is carried out on an AC basis, AC current. The output may be conventional sine wave or a square wave. Many electronic power sources allow the AC waveform to be adjusted. So you're adjusting between a negative and a positive, and that gives you a cleaning ability as well as it's also a penetration because it's putting heat into it as well, into the body of the power sources. May allow gas flows to be started before the arc is struck, and after the arc has been extinguished, the weld has been finished. The pre and post heat technique is very useful in reducing contamination by the weld by atmosphere. So it's what it's saying is you're given a gas before the weld starts, just to provide that protection from the atmosphere of the weld pool, and it's doing the same after it stops welding, just to let it cool down slowly and solidify before the gas disappears. You must maintain that gas shielding, which is important to keep the atmosphere away. Standard TIG torches, which may be air-cooled or water-cooled. Generally, they're water-cooled because you're welding at around about 150 amps for TIG welding aluminium. Much lower for a stainless steel and mild steel. It's only about 50, but generally up at 150 amps, you need a water-cooled torch, which tends to make it a little bit heavier. Different types of tungsten may be used for TIG welding, and these are pure tungstens or zirconiated, thoriated, serrated, but zirconiated is the most usual one for AC welding, which is for aluminium. The process must be autogeneous, so you don't need to add a filler wire, but in general speaking, you do add filler wires. So it's a bit of a repetition on this one. I don't need to go into all that. There are some for some applications where people want a much cleaner weld, the helium is added, but we tend to stick away from the helium at this moment in time because of its rarity and difficult to get hold of. Practical considerations: selection of TIG wire, as with MIG. Filler metals are normally chosen on a chemical composition and as closely as possible to the base material. And usual check what it's. So that's a bit of a repetition there. Cleaning and degreasing, so it's going through the same process you went with through MIG. Ordinary steel brushes shouldn't be used. Obviously, it's going to introduce oxides into the material, and it will corrode. So that's why we suggest using stainless steel for preparation of the weld. It's necessary to prepare the tip of the tungsten, usually by grinding, and this controls the stability of the arc. It's not like a normal TIG for stainless steel or mild steel. It tends to be very sharp point. On AC, it tends to get a balling effect, as you saw in the picture at the very beginning, and that's quite common. You're never going to maintain a sharp point on an AC tungsten. So there's quite a bit of repetition from MIG welding. It's exactly the same sorts of things. So I've been repeating it. Yeah, so it's all quite repetition. It's just because there's two different slide packs added together, cracking. So the same thing for TIG welding. Obviously, solidification cracking is an issue. Porosity is another issue. Not so much with TIG welding, and so we said about touching down a tungsten. So that contamination will show up on an X-ray alongside any porosity that you have. Thanks for your attention.